Have you ever really thought about what happens when you stir salt into a glass of water? I mean, it just seems to vanish. But what's really going on under the surface is this incredible, invisible drama. So today, we're going to put on our microscopic goggles, and we're going to step right into the aqueous laboratory to understand this hidden world of ions, electrolytes, and all the forces that control how stuff behaves in water. So let's start with a really simple mystery. It's an experiment you could literally do in your kitchen. You set up a basic circuit with a light bulb, stick the wires in a glass of salt water, and bam, the bulb lights right up. But then you do the exact same thing with sugar water, and you get nothing, not a flicker. The circuit is dead. So what gives? It's the same water, same bulb, same everything. What's the secret ingredient here? Well, this puzzle goes all the way back to the legendary scientist Michael Faraday. What he figured out basically changed chemistry. He realized the secret isn't the water itself, it's what you dissolve in it. Just look at the two pictures here. The salt water on the right is just teeming with these tiny charged particles, right? These positive and negative ions are just zipping around, free to move. They're like a living bridge for electricity. But now look at the sugar water on the left. The sugar molecules are just there, floating around whole. No free ions, no bridge. The electricity hits a dead end. Okay, so let's really get into the science behind this shocking kitchen experiment. You know, the entire reason that light bulb glows comes down to this one single powerful word: electrolytes. Salt water completes the circuit because salt is an electrolyte. It's a substance that makes an electrically conducting solution when you dissolve it in something like water. And sugar? Well, it's just not. But here's the thing. It's not just a simple yes or no, electrolyte or not. It's actually more of a spectrum, a whole range of possibilities. Let's start at the zero end of that spectrum. This is our sugar water, a perfect non-electrolyte. When sugar dissolves, the molecules spread out, sure, but they stay completely whole. They don't break apart, they don't carry any charge. And with no mobile charges, electricity just can't flow. That light bulb stays dark. Okay, now let's move into the middle of the spectrum. Here we find weak electrolytes, and a great example is acetic acid, the main ingredient in vinegar. When you put acetic acid in water, a tiny fraction of its molecules, we're talking less than 5%, will actually break apart into ions. Most of them stay intact. So you've got some charge carriers, but not very many. The result? It's a pretty poor conductor. Our light bulb would probably just give off a really faint, sad little glow. And finally, we get to the other end of the spectrum, the strong electrolytes. This is our table salt, sodium chloride. When this stuff hits the water, it doesn't just kind of break up, it separates almost completely into the sea of free-moving positive sodium ions and negative chloride ions. The water is now totally saturated with charge carriers, creating a superhighway for electricity. And that is why our light bulb shines so bright. And this right here, this slide just pulls it all together beautifully. You can see the whole landscape. On the left, at 0% ionization, you've got the non-electrolytes. In the middle, with just a little bit of ionization, are the weak ones. And way over on the right, getting close to 100%, are the strong electrolytes. The whole key is understanding the degree of ionization, how much a substance really breaks apart into ions when it's in water. And for strong electrolytes, like salt, that number is everything. We're talking about a near total breakup. It's this massive, almost complete release of charged ions that turns a simple glass of water into a seriously powerful electrical conductor. Okay, so we get that it happens. But the real question is how? How can plain old water possibly tear apart a solid salt crystal that's held together by these huge forces? To see that, we've got to shrink ourselves down and watch the whole thing happen step by step. The story of a salt crystal dissolving is kind of like a three-act play. Act 1, we start with the solid crystal lattice. Act 2, water shows up and acts like a powerful dielectric shield. And for the finale, Act 3, the ions are set free and stabilized in a process called hydration. All right, Act 1, the solid lattice. Now, this is a really critical point. A salt crystal isn't made of neutral little molecules. The positive sodium ions and negative chloride ions are already there as separate things. They're just locked into this super-ordered grid by incredibly powerful electrostatic forces, positive attracted to negative. And because they're locked in place, they can't move. That's why a solid chunk of salt won't conduct electricity at all. And now for Act 2. Enter water. The moment that crystal hits the water, water molecules just swarm all over it. And see, water has this sort of hidden superpower. Its special structure lets it get right in between those ions and just dramatically weaken the electrostatic glue holding them all together. And here's that superpower, as a number: 80. Water has what we call a dielectric constant of about 80. And that is an incredible number. What it means is that water reduces the attractive force between the sodium and chloride ions by a factor of 80. That immense force that held them in a solid crystal, suddenly it's so weak that the ions can just kind of drift apart. And this leads us to the grand finale, hydration. As soon as an ion breaks free from the crystal, it gets mobbed by water molecules, and you can see how perfectly they do it here. For a positive sodium ion, the negative oxygen ends of the water molecules all point in. For a negative chloride ion, the positive hydrogen ends point in. This creates a stable little hydration shell, like a protective bubble. It insulates the ion, and, most importantly, it stops it from getting pulled back into the crystal. Now they are truly free, totally mobile, and ready to carry a current. Okay, so let's just clarify a tiny bit of terminology, because it's important. The process we just saw with salt, where ions that already existed just separate, that's technically called dissociation. But for weak electrolytes like acetic acid, which start out as whole neutral molecules, the process where water forces them to split and create new ions is called ionization. So dissociation is just separating what's already there. Ionization is actually creating something new. And that difference between separating and creating is really key, especially when we look at those weak electrolytes again. For them, ionization isn't a one-way street. It's more like a constant, dynamic negotiation. It's an equilibrium. This seesaw is the perfect way to picture it. In a solution of, say, vinegar, some of the acetic acid molecules are constantly breaking apart into ions, but at the exact same time, other ions are bumping into each other and reforming back into molecules. It's a two-way street, a dynamic equilibrium. And as you can see, the seesaw is heavily tilted toward the side of intact molecules. That's why there are so few free ions hanging around to conduct electricity. So, we've looked at non-electrolytes, strong electrolytes, and this dynamic balancing act of the weak ones. Now, let's just pull it all together into one single, unified picture. This flowchart basically tells the entire story we just went through. We start at the top, you put some matter in water. First question, does it form ions? If the answer is no, boom, it's a non-electrolyte. End of story. If yes, it's an electrolyte. Then the path splits again. How much does it form ions? If water wins the fight and it breaks apart almost 100%, it's a strong electrolyte, stabilized by those hydration shells. But if the molecule's internal bonds are strong and it only ionizes a little bit, it's a weak electrolyte, stuck in that dynamic equilibrium. It's all a beautifully logical flow. So, if you take one thing away from all of this, let it be this: the glowing light bulb, the dim one, the dark one, all of these big, visible, macroscopic things we can see are a direct result of what's happening at the tiny, invisible, microscopic level. The electrical state of that solution, it dictates everything. And, this invisible dance of ions isn't just some weird lab experiment. It's happening in the ocean, it's happening in your blood, it's how batteries work, it's how your nerves fire. It is everywhere, all the time. And it kind of makes you wonder, doesn't it? What other incredible microscopic dramas are unfolding all around us, hiding in plain sight?